Now going to give her talk.
Good morning, everyone. My name is Maria Pantopoulou, and I'm a master's student at Purdue University. And this talk today is going to be about our work based on wireless quantum key distribution for small modular reactor secure communications. Before I start the presentation, I would like, of course, to thank the other members that contributed to this work. So I'll start the presentation by talking about the motivation of the specific project, which is related to the need for wireless communications for advanced reactors. This can be achieved by implementing a quantum key distribution protocol, as quantum computing can be really advantageous in many cases due to its properties. Then I will briefly talk about the BB84 protocol that we used, and I will continue with the development of a channel attenuation model, which we used in order to calculate the attenuation of the transmitted signal due to several weather conditions in free space. Then I will provide some results we got from Sequence, which is an open source Python software package developed in Argonne National Lab, and we used it in order to calculate the time that is needed for the protocol to be completed. Finally, I'll close the presentation with some conclusions and ideas for future work. So, as everyone knows, small modular reactors are now under development and are going to be used for distributed energy resources applications. The ability to communicate with small modular reactors off-site is key to enabling remote operations, which is an appealing prospect for low operation and maintenance costs, and also to ensure user convenience. So, in order to have this fully remote control, we need a two-way transmission exchange between the reactor and the user to whom the facility sends the reactor state data. And for this communication channel, we need a high level of security. To achieve this high level of security, we can use a quantum key distribution protocol paired with an advanced encryption standard protocol to generate the communication cipher. So now let's see how we can actually have secure communications with small modular reactors. As you can see in the figure here, whenever we want to send reactors state data, a key is generated and distributed through a quantum channel, the green one in the figure. So we use a quantum key distribution protocol to generate a key, and using this key we can then encrypt the message that we want to send, let's say, to a remote user. So QKD is often paired with an advanced encryption standard protocol, and using a conventional classical channel we can easily encrypt the message and send it to the remote user who possesses the same key, so he can then decrypt the message. So today I'll talk about the BB84 protocol, which is a very well-known protocol developed in 1984 by Bennett and Brassard. The main idea of the protocol is to encode every bit of the secret key into polarization states of entangled photons. The basic steps of the protocol are three. First of all, a QKD source generates a sequence of bits and then chooses randomly bases in order to encode these bits into photon polarizations. Then the two receivers actually do the same thing. They choose randomly bases in order to measure the pulses, and also they record their measurements. The final step of the protocol is that they publicly reveal through the conventional classical channel the bases that they use to measure the pulses. And here we have two cases. In the first case, they have chosen the same base to measure the pulse, and that means that the measurement is correct. So this bit can be used for the final key. In the other case, they have chosen different bases, so their measurement is incorrect and this bit is thrown out. So as a testbed for advanced reactor communication, we can use Metal Facility. Metal Facility is an intermediate scale liquid metal experimental facility in Argonne, and many experiments that are conducted there actually assist in the development of advanced reactors. In Metal Facility, there are 4 test vessels and more than 1,000 sensors, and also there is live stream data feed, for which a 256-bit key along with an advanced encryption standard protocol is recommended. In the one photo of this slide, you can see the Metal Facility, and in the other one, Metal Health Dataset, which includes some parameters for the vessels. So in the left part of this slide, you can see the existing communication network in Metal Facility. So as I said before, we have 4 test vessels and many sensors that measure parameters like temperatures and pressures of the vessels. So these values are then sent to the control room and need to be distributed to several applications that most of them are in the cloud. In the right part of the slide, we can see the envisioned secure communication in Metal Facility. So let's say we want to send the Metal Health dataset to a remote user. So we can generate a key using a QKD protocol, and along with an advanced encryption standard protocol, we can encrypt the message that we want to send to the user, and then the user easily decrypts the message as he possesses the same key. Here you can see an example. So here we use the Microsoft Advanced Encryption Standard implementation. Let's say we want to send the values of the parameters in the mental health dataset. So we first generate a 256-bit key using a QKD protocol, and we also use an advanced encryption standard protocol to get the encrypted text that we're gonna send to the user. So the user, as I said before, possesses the 256-bit key, the same key, so he can easily decrypt the message and get the recovered text, which, as you can see, is identical with the input text. So the main point of this presentation is to see why we need wireless QKD for long-distance communications. So in the literature until now, most of the work has to do with QKD implementations that use optical fiber. However, optical fiber has many limitations. So when we have conventional QKD that relies on optical fiber channel, we have 0.5 dB per kilometer attenuation for telecom wavelength, and the losses of the transmitted signal are really high for more than hundreds of kilometers. Also, for a lane dedicated fiber optic channel, this option is limited only for distances less than tens of kilometers. Another option that someone can think about is free space optical QKD. However, the problem with this option is that due to some atmospheric conditions, the attenuation of the signal is really high, so this option is limited only, let's say, for 500 meters. So a good alternative to this problem can be wireless QKD. So we focused on this work on X-band microwave signals from 8 to 12 gigahertz, which are used for radar and satellite communications. And we wanted to estimate the channel losses due to several weather conditions in free space. So before proceeding with experimental realization, we wanted to investigate how feasible it is to develop a QKD protocol over a 500 kilometer distance using sequence computer simulations. In this slide, you can see the three conditions that should be examined. So first of all, we want to see what happens when the weather is clear. So even when the weather is clear, we can have attenuation due to dry air and water vapor. We want to evaluate the attenuation for different values of pressure and temperature and humidity. So for signals in frequencies from 1 to 1000 gigahertz, we can use the formula that is shown in this slide, which is recommended by ITU. And in this formula, F is the frequency of the signal, and the other two parameters are the imaginary parts of frequency-dependent complex refractivities of oxygen and water vapor, respectively. In the condition of cloudy and foggy weather, we also need to see what's happening there, because clouds and fog consist of small droplets that of course affect the transmission of the signal. So for signals in frequencies up to 200 gigahertz, we can use the formula here where M is the water density of fog or cloud, and K is a specific attenuation coefficient. Last but not least, we have the rainy weather condition. So this is a major challenge in air satellite communications, as when we have, for example, a heavy rain, that means we can even have complete loss of the signal, and we should terminate the communication. So for signals in frequencies from 1 to 1000 gigahertz, we use this formula here where K and A are frequency-dependent coefficients and R is the rain rate. So we used MATLAB's communication toolbox in order to calculate the attenuation of the transmitted signal for a specific path length and specific frequency. So in all the three conditions I mentioned before, the attenuation drops exponentially as the altitude increases. So this is the reason why we focused only on the first 30 kilometers of the path length. The path length includes the troposphere, the lower stratosphere, and upper stratosphere. So first we need to do some adjustments for the temperature and pressure parameters in order to get the correct values for the attenuation. And for this, we actually used NASA's atmosphere model. So we estimated the losses of the transmitted signal of frequency 10 gigahertz over a 500 kilometer distance, and we examined what happens in 4 different weather conditions. when we have clear sky, light rain, moderate rain, and finally heavy rain. So in this slide, you can see the results we got from MATLAB, which show the attenuation of the transmitted signal in all the 4 different conditions that we examined. So in the first figure, we see what happens when the weather is clear. So in this condition, the highest attenuation that we get is almost 0.007 dB per kilometer in the first kilometer. And after that, you see that the attenuation decreases as the altitude increases. So in the second figure, we see what happens in light rain condition. The highest attenuation here is almost 0.12 dB, and after the 7th kilometer, the attenuation decreases. In the case of moderate rain, the maximum attenuation is about 0.25 dB, and in the last case of heavy rain, we get, of course, the maximum attenuation, which is about 0.4 dB per kilometers. So in the 3 last conditions with rain, you can see that after the 13th kilometer, the attenuation is very small or even equal to 0. And this is because this is the average rainstorm height. In this table, you can see what we actually show in the figures before, that the highest attenuation that we got was for heavy rain and the lowest was for clear sky. So next step was actually to create the quantum and classical channel and also the 2 nodes that we need. So we used Sequence, which is, as I said before, an open source Python software package developed at A&L, and we actually created the classical and quantum channel. By default, Sequence uses as quantum channel optical fiber, but we could change this parameter in order to have a wireless channel. So we also changed some other parameters for the path length that we wanted, and the frequency of the signal, and the losses that we had from MATLAB. And also I should mention that Sequence implements the Cascade protocol, which is an error correction process that is used to actually achieve a 0% error rate for the key between the 2 parties that communicate. So after we made all these adjustments for our model, we wanted to calculate what happens for a 10 gigahertz signal. And also we assumed that there is a signal depolarization of about 3%, as ice and rain depolarization can be a problem for signals in frequencies above about 10 gigahertz. So we use Sequence to simulate what happens for a 256-bit key, and we performed 100 iterations to get an average protocol time, and this time includes the generation of the key, the transmission, and also the correction. So in this table, you can see the average time that we got for the 256-bit key for all the 100 iterations, and as you can see, the highest time that we obtained was 560 milliseconds for the heavy rain condition. So in nuclear motor systems for temperature, more particularly, we have that the time delays are almost 1 second. And all these timings here, that are shown in this table show actually that these timings are compatible with the requirements for real-time communication with SMRs. So to conclude, in this presentation, we actually saw that we can extend the communication range for quantum key distribution if we change the optical fiber and we use a wireless quantum channel. Using MATLAB, we also obtained results for the attenuation of the signal, and we saw that in clear sky we have less than 1%, and in heavy rain less than 4.2% of typical losses in commercial fiber. And then we introduced these attenuation results into Sequence to get the average protocol time, which was less than 1 second in the heavy rain condition. So that means that wireless QKD is compatible with the requirements of real-time application with future SMRs. As an idea for future work, we actually want to investigate several approaches for experimental realization of wireless QKD, like for example, to have either a source, an optical source that also includes a converter from optical to microwave, or to have a microwave source for entangled photons. I would also like to acknowledge ARPA-E by Gemina program, Office of Naval Research, and GSG's Foundation that supported our work. And in case you have any questions, I would be really happy to answer them.
All right.